Good morning, everyone. So now our topic for today is joint probability distribution. In probability theory, the joint probability distribution is the probability distribution of all possible pairs of outputs of two random variables that are defined on the same probability space. The joint distribution can just as well be considered for any given number of random variables. First, we introduce the joint distribution for two random variables of characteristics of x and y. First is the discrete case. Let x and y be two discrete random variables. For example, x equals to number of courses taken by a student, and y is equals to number of hours spent in a day for these courses. Our aim is to describe the joint distribution of x and y. So, the joint distribution of x and y, both discrete, is defined by probability of x and y is equals to probability of x is equals to x and y is equals to y. And this is the marginal distribution of x and y, the formula x. Example number 1. The joint distribution of probability of x and y of x number of cars and y the number of buses per signal cycle at a traffic signal is given by the chart below. So, first is find the probability of x equals to y. B is find the marginal distribution of x and y. C, suppose a bus occupies 3 vehicles spaces and the car occupies just 1. What is the mean number of vehicle spaces occupied during a signal cycles? That is, find the mean or expected value of h of x and y is equals to x plus 3y. Solution number 1. The number of cars equals the number of buses if x is equals to y. Hence, probability of x is equals to y. So, the probability of 0, 0. So, the x and the y. 0, 0. Then the 1, 1 plus 2, 2. So, sa 0, 0 is 0.025 plus 1, 1, 0.030 plus 2, 2 is 0.050. So, 0.025 plus 0.030 plus 0.050 is equals to 0.105. Solution B. To find the marginal distribution of the x and y, first is the marginal distribution of the x. So, x, adding the row values yields the marginal distribution of the x values. So, sa 0, 0.025 plus 0.015 plus 0.010 is equals to 0.05. So, sa 1 is 0.050 plus 0.030 plus 0.20 is equals to 0.1. And hanggang sa 5, 0.050 plus 0.030 plus 0.020 is equals to 0.01. So, the mean number of cars is 0 times 0.05 plus 1 times 0.10 plus 2 times 0.25 plus 3 times 0.30 plus 4 times 0.20 and plus 5 times 0.10 is equals to 2.8. So, the marginal distribution of the x is 2.8 and the marginal distribution of the y is, first is a y 0, 0.25 plus 0.050 plus 0.125 plus 0.150 plus 0.100 plus 0.050. is equals to 0.50 hasta sa 2. So, the marginal distribution of the y is 0.7. 8 times rin yan sila. So, solution C, let x and y denote the number of cars and buses at a signal cycle. That the number of vehicle spaces occupied is h of x and y is equals to x plus 3y. Hence, the mean number of spaces occupied is then e times h x and y is equals to e times x plus 3y. So summation is x plus 3y times the probability of x and y. So x equals to 0 plus 3 times 0, and sa p xy 0 is 0.025. So 0 plus 3 times 0 times 0.25, then plus 0 plus 3 times 1 times 1, the x and y of 0 and 1 is 0.015. So times 0.015 hanggang sa 5 plus 3 times 2, and the x and y of 5 is 0.020. So the answer is 4.90. Note that e times h x and y is equals to e x plus 3y can also be computed from the result of e x plus 3y using the marginal distribution of x and y. So the x value is 2.8 plus 3 and the y is 0.7. So 2.8 plus 3 times 0.7 is 4.90. Next is a continuous case. The variate continuous distribution. Let x and y be continuous variables. The joint probability density of x and y denoted by f of x and y satisfies f of x and y is greater than or equal to 0, and the integral of x and y times dx dy equals to 1. So the graph of x and y times f of x and y is a surface in three-dimensional space. The second condition shows the volume of the density surface is 1. So the properties: if x and y are two continuous RVS with density of f of x and y, then the probability of x and y is equals to integral of f of x and y dx dy with the lower bounded of a, which is the volume under density surface above a. The marginal probability density function of x and y are respectively fx of x is equals to integral of f of x and y dy with the upper bound of infinite and the lower bound is negative infinite. So the mean expected value of h of x and y is the micro hx and y is equals to integral h of x and y times f of x of y dx dy. So example number 1. Let x and y have the following joint PDF. f x and y is equals to 2 over 9, for x is greater than or equal to 0 and y is greater than or equal to 0, and x plus y is less than or equal to 3. So find the marginal of PDF of f x of x. For x is the interval of x is 0 and 3. So fx of x is equals to integral of f of x and y dy with the upper bound of infinite and the lower bound is negative infinite. So the f of x and y is equals to 2 over 9. So integral of 2 over 9 dy with the upper bound is infinite and the lower bound is negative infinite. The new equation of this is the integral of 2 over 9 dy with the upper bound of 3 minus x and the lower bound is 0. 3 minus x, we know that the maximum value of y is 3, and don't forget we're conditioning. The y cannot go above 3 minus x because of the x plus y is less than or equal to 3. So next is 2 over 9, the 3 minus x is change the dy. So 2 over 9 times 3 minus x. So the final answer is fx of x is equals to 2 over 9 times 3 minus x, for x is the interval of x is 0 and 3. Example number 2. In previous example is find p of x is less than to y. So p is x less than to y is equals to double integral of f of x and y dx dy. So sa first integral is there is the upper bound is 3 half and the lower bound is 0. 3 half because they cross between 1 and 2, so the interval of outer integral is 0 and 3 half. And then the internal integral is 3 minus x. The upper bound is 3 minus x, the lower bound is x of 2 over 9 dy. So 3 minus x same doon sa first example, then so sa lower bound of y is x. The interval of the inner integral is x and 3 minus x. The integral of 2 over 9 dy with the upper bound of 3 minus x and the lower bound is x. Change the dy to 3 minus x and x it times 3 minus x. So the integral of 2 over 9 times 3 minus x dx with upper bound of 3 half and the lower bound is 0. So x times 3 minus x is 3x minus x squared. So 2 over 9 times 3x minus x squared with the upper bound of 3 half and 0. Substitute the 3 half to x. So 2 over 9 times 3 half minus 3 half squared. And 3 times 3 half minus 3 half squared is 9 over 4. So 2 over 9 times 9 over 4 is equals to 1 half.
Hello everyone, so today I'll be presenting an overview of marginal and conditional probability distributions. So these concepts are fundamental in probability and statistics, with applications in areas like machine learning, weather prediction, and healthcare. So let's start with an introduction. Probability distribution are tools for understanding events. Marginal probability focuses on the likelihood of a single event, while conditional probability explores relationship between one or two or more events. marginal probability. So it is the probability of a single event occurring without considering other variables. It is derived by summing or integrating over all possible outcomes and other variables in a joint distribution. So here are the formulas for marginal probability. For discrete variables, we sum the probabilities of all possible outcomes. And for continuous variables, we integrate over the probability density function. So a simple example of marginal probability is if 60% of a population owns pets, it just states that the value that represents the marginal probability of owning a pet. So now, let's move on to the conditional probability. It is described as the probability of one event occurring given that another event has already occurred. So these are the formula for conditional probability. The formula can also be expressed for continuous variables using joint and marginal probability density function. So an example is, suppose that the probability of rain today is 30% and the probability of it being cloudy is 50%. So using the probability, we can calculate the likelihood of rain given that it is cloudy today. So another example, in retail, suppose that there are 40% of customers that buy alarms and 20% buy both alarms and bucket seats. So the conditional probability of buying bucket seats given that the purchase of an alarm is 50%. So in healthcare, conditional probability is crucial. For example, the probability of breast cancer increases from 1 to 8.3% if a mammogram is positive. So this shows how testing influences probabilities. So these concepts are applied widely in machine learning to classify data, in weather forecasting, and to predict conditions, and in healthcare to diagnose diseases effectively. Visual aids like Venn diagrams and histograms help represent probabilities. These tools makes it easier to understand the relationship between events. So, in summary, marginal probability evaluates single event while conditional probability focuses on the relationships. So together, they provide a powerful framework for analyzing and making data predictions. So that's it. Thank you for your attention, and I am happy to take any questions or to discuss the examples further.
Next is the multivariable equation. It involves two or more variables. These equations are common in algebra, calculus, and applied sciences. Below are some examples and context. A multivariable equation can be written as f of x sub 1, x sub 2, and so on is equals to 0, where x sub 1 and x sub 2 are variables.
Today, we'll explore how linear functions combine random variables and their significance in engineering data analysis. So, we will discuss what is a linear functions of random variables. So, a linear functions of random variables combines two or more random variables using linear operations. This concept is a crucial in engineering data analysis, particularly signal processing and predictive modeling. A linear functions of random variables uses additions, subtractions, and scalar multiplication to combine variables. A random variable is a variable whose value is determined by chance. A linear functions of random variables transform it using this formula. Y is equal to ax plus by. Here, x is the original random variables. A is a constant multiplier or scaling factor. B is a constant that shifts its values. Y is the new random variables after the transformation. So, K properties, 1 is a mean of a linear function. The mean of y is equal to ax plus b is equal to a mu x plus b. So, mu x is the mean of x. 2. Variance of a linear functions. The variance of y is sigma squared y is equal to a squared sigma squared x. So sigma squared x is the variance of x. Note, adding b does not affect the variance because it only shifts the distribution without spreading it out. So this is the example problem. Let's say a random variable x has mean mu x is equal to 5. The variance is sigma squared x equal 4. Now, transform x using the formula y is equal to 2x plus 3. So, mean of y is mu y is equal to 2 times 5 plus 3 is equal to 13. While variance of y is sigma squared y is equal to 2 squared times 4 is equal to 16. Conclusion: the linear transforms of random variables help us adjust, predict, and analyze data in a structured way. Always remember the formulas for means and variance transformation, and you'll be all set. Thank you.
Hey everyone! Today, we're going to delve into the world of engineering data analysis, specifically focusing on the general functions of random variables. First, let's understand what a random variable is. A random variable is a variable whose values are the outcomes of a random phenomenon. Simply put, it's a way to assign numbers to different outcomes of a random process. For example, consider a rolling dice. The outcome can be 1, 2, 3, 4, 5, or 6. Here, the random variable, let's call it x, to represent the result of the dice roll. Now, on to the general functions of random variables. These functions are essentially ways to transform random variables to understand and analyze them better. For the probability distribution function, or PDF, it describes the likelihood of different outcomes. It is written as fx of x is equal to p of x is equal to x, which means the probability that the random variable x equals a specific value of x. The cumulative distribution function, or CDF, gives the probability that a random variable is less than or equal to a certain value, and hence it is written as fx of x is equal to p of x less than or equal to x, which means the probability that x is less than or equal to x. Let's illustrate this with an example. Imagine we have a simple game where you roll a dice, and if the result is 4, 5, or 6, you win a prize. We can define a random variable y, where y is equal to 1 if you win and y is equal to 0 if you don't win. To understand this better, let's look at the PDF for y. P of y is equal to 1, the probability of winning, which is the probability of rolling 4, 5, or 6. This is calculated as P of y is equal to 1 equals to 3 over 6, or 0.5. For P of y is equal to 0, the probability of not winning, which is the probability of rolling 1, 2, or 3. This is calculated as P of y is equal to 0 equals to 3 over 6, or 0.5. Now, let's look at the CDF for y. The Fy of 0 is the probability that y is less than or equal to 0, which is just P of y is equal to 0 equals to 0.5. For Fy of 1 is the probability that y is less than or equal to 1. This includes both P of y is equal to 0 and P of y is equal to 1, which is 0.5 plus 0.5 is equal to 1.0. To sum up, random variables are fundamental in analyzing random phenomena, and their functions like PDF and CDF helps us to understand the probability and distribution of outcomes. I hope this example made it easier to grasp the concept. Thanks for watching.